Now, obviously, when we deal with gases, especially again in the life science, we're never really dealing with pure gases. We often deal with gas mixture. And whether you are someone interested in marine biology and you're doing a lot of scuba diving, of course you have a gas mixture in your tank. If we do chemical reactions, let's say we want to make ammonia because we are interested in making fertilizers, then again we mix nitrogen and hydrogen and we form ammonia, which is also a gas. So we deal with gas mixtures in many circumstances. So for ideal gases, what we can do is we can use the ideal gas law and apply the ideal gas law to each of the species present in the mixture. So for example, if we have a gas which is represented by different molecules of different colors, so just to represent different species, we have I think green molecules and red molecules and blue molecules, and I'm going to call the blue one A, the red one B, and the green one C. We can apply the ideal gas law to each of these species. So we would write P sub A is equal to N sub A, number of moles of A, times RT over the volume in which the whole mixture is contained. But now what P sub A is the pressure that is just due to A. Okay, it's the pressure that is just due to the component A, assuming A was alone in the gas mixture. And assuming it's alone actually is okay, because when we have ideal gases, remember, ideal gas molecules do not interact, so they ignore each other. So each molecule behaves independently of the other. So whether this molecule here ignores just the blue molecules or the blue and the red and the green is the same. So this is a good approximation. And P sub A we're going to call the partial pressure of A. Now, of course, we have B and C present. So what we can do is say that the total pressure, P, is the sum of the pressure A, PA, plus that PB plus PC. So the total pressure in a gas mixture is the sum of the partial pressure. Now, either one of these equations, this one here, for the sum of the pressure is the total pressure, or the equation PA NART over V, these two equations are known as Dalton's law. Now, another way to make use of this relationship is if we use the same equation for A, B, and C. Okay, for example, we can write P sub B is equal to N sub B times RT over V. P sub C equals N sub C times RT over V. When I add PA plus PB plus PC, what I'm really doing is putting NA plus NB plus NC, all these times RT over V. Okay, that would be equal to the total pressure P. So what we see is that now if we take any one of those, let's say we take PA, which is NA RT over V, and we divide by P, which is NA plus NB plus NC times RT over V, all we're going to have left is NA over N, N being NA plus NB plus NC. The RT over V, of course, which is here, cancels out with the RT over V, which is here. Okay. So now what we have is we have yet another relationship, which is PA over P, the partial pressure of component A over P is the number of moles of A or the total number of moles, and that's what we call the mole fraction. So another way to write Dalton's law is here, is the partial pressure of A is the mole fraction of A times the total pressure. So what you're going to have to do is you're going to have to learn how to memorize, of course, these three equations, you know, and best is to just memorize the gas law and understand the concept that when we use Dalton's law, we basically use the ideal gas law for each of the species, but instead of having for each species the total pressure, we have the pressure due to that species. Let's look at one example. So here we have a sample of air at 25 degrees Celsius. And this air is under a pressure of 0.88 atmospheres, and we know the volume is 17 liters. Now, we're going to assume in this problem that the air only contains oxygen and nitrogen. And that's obviously a pretty good approximation because we know that CO2 and argon and even water, the water vapor, which is often present in air, are present in much smaller quantity than O2 and N2s. So assuming we have a mole fraction of oxygen that's 21% or 0.21, and assuming that these gases behave ideally, what we want to do here is calculate the partial pressure of N2 and the number of moles of N2 in this sample. So partial pressure of nitrogen. Well, the way we're going to write this is using the expression shown here. The partial pressure of nitrogen, P net, is equal to X net, which is the mole fraction of nitrogen times the total pressure P. Now again, remember we have to be careful with the units. As long as if we use some unit for P here, then we're going to get the same unit here, right? Mole fractions are ratios of moles, it's unitless, okay, so that's good. So if we have P equals 0.88, I need to get the mole fraction of nitrogen. Well, if I only assume that I have nitrogen and oxygen present in the mixture, then the sum of the mole fraction of nitrogen plus oxygen is 1. Therefore, X nitrogen is 1 minus that of oxygen, which is therefore 0.79. So I take 0.79, mole fraction of nitrogen, multiplied by 0.88, and I get 0.6952. And yesterday we talked about significant figures, 0.6952. Let's see, we have two significant figures, so we can use two significant figures. Okay, so 0.70 atmosphere would be the correct answer for the partial pressure of nitrogen. Now, the number of moles of nitrogen, to get number of moles of nitrogen, all I have to do is use the definition of the partial pressure right here. Partial pressure is the number of moles of nitrogen times RT over V. Okay, so I know R, obviously I know the temperature is 25 degrees Celsius. I'm going to change that into Kelvin, because remember that we always use Kelvin when we use the L gas law. So this is 298.15. Since I'm using atmospheres for the pressure, since I had it in atmospheres, I'm going to use 0.08206 liter atmospheres per mole Kelvin for R. This is the R value. And then the volume here, V, will be in liters. Okay, so when I do that, then the number of moles is obtained in moles, and everything should be fine. All the units cancel out. We check this out. Atmospheres. We had liters on the top, liters here. Then we have Kelvin on the here, Kelvin there. They cancel out, and then we have 1 over mole, and that's mole, and then we get 0.48. Okay, so note that when I did this calculation, okay, even though I knew that the pressure of nitrogen in the final, when I report the pressure, I use 0.70 with two significant figures. When I calculate the number of moles of nitrogen, I use more figures to make sure that I don't basically perpetuate these truncation errors that could eventually affect my final result for N. So when I do that, I get a number which is not 0.48. It's got more figures than that. But then again, at the end, I will use two significant figures, because in this calculation here, I know that the volume was known with two significant figures, and I know that this pressure was also known with two significant figures. So at the end, I have to have just two significant figures.